Hi, everybody. Looks like we have more people in here, so let's go ahead and get started. What are we doing this week? So we have done Unit 11 for the most part. We're going to do acids today and finish it up. Then we're going to move on to Unit 12. We also talked about lab number 3 yesterday. Not really much to say about lab number 3 other than it's due on the 12th next week, so you can see that below. Quiz number 5, which is units 9 and 10, is due tonight. Try and get that done before the deadline if you can. There'll be a last call sometime tomorrow to get your quiz in. You don't want to really be doing your quiz on Friday night. I mean, not that we're all going out and doing other things, I assume, but yeah, there will be a Unit 11 quiz coming up. That'll be quiz number 6. Yeah, let's just get right into it. That's really all I've got. Oh, and yeah, yesterday was my birthday, so hooray. I'm on the wrong screen. This is not the right screen. How is Among Us? I'm the worst imposter, though I won 2 of my 3 games, so... I really enjoyed it. I had a great time. A lot of people had fun. I just dropped my pen. Hold on. Oh. Trying to pick it up with my feet, and that's not super effective there. No, Among Us is great. I immediately panicked and reported the wrong person and their color, and everyone got confused, so I must be lying. And out the airlock, my poor little green guy went. Whee! No, I just heard meow question mark from the side of my ears. Yes, it's a cat. So you might hear her in the background. Excuse me. All right, let's talk about acids. What is an acid? So, an acid is a category of types of chemical compounds. Okay? So, when I say, oh, it's an acid, what that means is specifically it meets this criterion. An acid contains H+. Now, some things might be called acid, and in order for that statement to make sense, they still must follow the. They still must fulfill this. Would you stop it, Maya? My God, she just won't shut up in the background, and all I hear. No, get out of here. Oh my goodness, just a second. No, you're not allowed to be in here yowling your head off while I'm teaching. I have broken my cat's heart because I have locked her out of the room. Oh, she's gonna. As soon as I start, she just starts yowling. It's like, nope, I cannot have that in in my lecture. Where the hell was I? I was on acids have H+. If you call something acid, even colloquially, they still tend to follow this definition. So like LSD, which I forget the actual chemical name for, but it ends in acid, and it actually has an acid group in it, an H+ that can come off. Now, when you put an acid into water, it will dissociate, and one of the pieces that will dissociate is the H+, and the other thing that is left over is the anion. Now, there are always enough H+ on the acid that you are looking at to neutralize whatever the charge of the anion is. So, depending on the anion that you have in your acid, so this one I have a -3, but this one I have a -1, I need a different number of H pluses to create a neutral effect. So, in other words, what we're kind of doing is treating these as if they're ionic, because they do. They ionize into ions, but they only contain nonmetals. And so, acids are kind of like the gray area between covalent and ionic compounds. Specifically, though, they involve hydrogen. So, since I had a -1 charge on chloride here, I need 1 H+ to make HCl. Because I had a 3- charge on phosphate, I need a plus charge on my hydrogen, and 3 of those hydrogens to make my phosphoric acid. Now, the name that we are going to give an acid is going to depend on the anion. So name depends on the anion. I could still hear her crying through the door. She just wants to be hugged so badly, you guys. Oops, I didn't know that was the last part of this. So depending on what anion we have, we're going to pair it with H+, but depending on the name of the anion, we're going to determine the name of the acid that we are working with. Now, there are 3 categories of acids, and so we're going to look at the name of the anion, see which category the anion falls into, and then name the acid appropriately. Now, this is sort of a weird case that might come up on occasion. In the context of this class, all acids that we are ever going to interact with will be aqueous. However, that being said, there are things to note about gaseous acids. So what we're going to do is we're going to look at the first set of naming rules that deal with gaseous atoms, and then we're probably never going to use it because you don't often see gaseous acid in the outside world unless it's like in a gas cylinder or something like that. So let's define some terms here that are going to help us discuss acids. So the first one's binary acid. Just like anything binary, binary means 2. And so if you have 2 elements in your acid, H+ and then some other nonmetal, you have a binary acid. Now, if the binary acid is a gas, here's how you name it. You just write the word hydrogen. And then oh my goodness, now the other cat is out there and they're fighting. What is with them? Okay, I have to put a stop to this. Sorry. Just a moment. Stop fighting! Get out of the door! What is wrong with you? No! No! Go on! Go on! Stop that! I'm trying to teach you. They were literally buried in the nook of the door when I opened it, on top of each other, like trying to bite each other's necks, because that's what they do when they play fight. Or angry fight. Okay. Yeah, because cats understand, right? I just clap my hands at them, and the loud noise scares them, and then they just run off and do whatever they're doing. They just want me to pick them up and hold them all the time. That's just the thing. Let me just start over wherever I was. Okay. So, if your acid that you're working with is both binary and is in the gas state, the first word that you're going to say is hydrogen. And then the second word that you will say is whatever the anion is with "ide." So we've already done this. We did this in the ionic naming section, and also a little bit in the covalent naming section too. So if I had HF, for example, let me get the pen out here. So if I had HF, and it was a gas, I would call this hydrogen fluoride. Just like if it was ionic. And you can do this with all of the compounds. So this would be hydrogen sulfide. And so on and so forth. You could use for any combination of hydrogen plus a nonmetal anion. Now, what if it's aqueous? This is going to be the rule that we're going to use the most. So this is the rule set that I would commit to memory. It's this one right here. If the acid is in the aqueous state, you say hydro. I'm gonna highlight this, but I'm gonna say the word blank. Ic acid. So everything that's in black on the screen is just the word that you say. But that highlighted part where it says anion stem, that's going to be the name of your anion minus the ide. So, for example, and that's one of the acids that we're going to name right there is hydrochloric acid. So, if I had this acid and it was aqueous, then the anion is chloride. We get rid of the ide, and what's left is the anion stem. So this would be hydrochloric acid. Or hydrobromic acid, or hydroiodic acid, so on and so forth. Now, there's actually one other ion that follows this, it's HCN. So, a better way to do this naming scheme, instead of calling them binary acids, is you could think of all of these acids as acids that have an anion that ends with IDE. And if your anion follows that rule, or I'm sorry, if your anion ends with IDE, it follows this rule on the screen. So cyanide ends with ide. So we're going to chop off the ide, and we'll put the rest of the stem into where it says anion stem. So this would, HCN would be hydrocyanic acid. Now, there are not that many anions that end in ide, so only HCN and then all the binary acids follow this. So that's why your text will talk about just binary acids. So that's the first naming rule, is hydroblankic acid if your anion ends with ide or it's a binary acid. Now, there's two other ones, and for those, they're all going to be polyatomic ions that make acids. And I don't know if it actually calls them Moxie acids on the slides. Actually, let's come back to this. It does, okay. I feel like, I mean, we've already done these examples, but if just really quickly to reiterate here. So the top two are gaseous and the bottom two are aqueous. Go ahead and type in the chat what you think the names of these are. Do the gas ones first and then do the aqueous ones. And then we'll go over the answer in just a second because now I'm just imagining that I'm hearing my cat. So I'm going to go check. Okay, I do not hear the cat, and I actually did open the door again because they were not there. They've just run off and are sitting in a box. All right, so let's see here. HBr, hydrogen. Oh, why did I open the door? Maya's immediately back. So this is a gas. We say hydrogen bromide and hydrogen fluoride. These down here are aqueous, so we use the hydroblankic acid rule. Hydrobromic acid. And hydrofluoric acid. There's confusion on the last section on the previous slide, so let's go back to the previous slide. What was your question here? The exception. So HCN is really the only exception here. This slide is kind of trying to note two different types of things that follow these formulas. The first is a binary acid, so that's just H plus and a nonmetal. And then the other type is if the anion ends in "ide." So if you meet either of those qualifications, and in fact, for the most part, they are the same qualification. If you meet those qualifications, you use the rules on this page. Now, there are two rules because one concerns itself over whether it is a gas or it is aqueous. And since we're going to be working with acid almost entirely in the aqueous state, we're really only going to be using this bottom rule. So if the anion ends in "ide," it ends with acid if it's aqueous. That's correct, yeah. Yeah, you do need the word acid. So that where that plus is, that is that is intended to be, here's another word that you add onto the end. So I have this water here, and Maya hates it when I spritz her with water. So I'm gonna have to buy like a squirt bottle and be like, nope, you do not get to meow at me right now. I will hug you later. Oh gosh, she's talking back to me in the hallway. My cats today. I don't want to yell at them because they're so sad when they look at me. But at the same time, I have to work, so I can't sit here and dote over the cat. Okay. So the next two sets of rules are for anions that end in "ite" and "ate." So let's write those down. Actually, I'm going to write them down in the other order here. So "ate" and "ite." Yeah, that's the other one. Pennies in a can. Maya especially hates water, though, so... Like, if I have just showered and I, like, shake my head and a little tiny bit of water goes everywhere, she runs away. All right, back to the naming rules here. Let's get through these rules so I don't have to keep talking about my cat here. So, the first rule that we're going to consider for oxyacids is if the ion that we're looking at ends in ATE, or 8, then here's the rule that you write. You're going to get the name of the polyatomic ion, but chop off the 8. And then whatever is left, you're going to append ic acid to it. Now, if the polyatomic ion contains ite in its name, it's the same thing, but you just remove ite and put less acid at the end instead. So these rules are very similar. It's just this is the difference here. 8 becomes ic acid, and ite becomes us acid. So you have the right idea, except we're actually going to talk about an exception for phosphorus and sulfur, because it makes it sound better, I guess. So instead of phosphic acid, it becomes phosphoric acid. But like nitric acid or acetic acid or so on and so forth. And so let's do a bunch of examples for that. Oh, there's one of the things that I just said right there. So, using your table of polyatomic ions, you have to look up what ion this is. Wow, that was a bad underline. So when this dissociates, I get H+, and that, I get everything else. It's going to have the opposite charge of my plus here, so it becomes minus. Now you got to look up the name for this thing. What is the name of that on the chart of polyatomic ions? That's acetate. Good. Now we follow the naming rules for acids. We would say, okay, it ends in 8, so I'm going to get rid of that. And then I'm going to add ic acid. And so there's the new name of our acid, acetic acid. Let's do another one. What's the name of this? So again, I got to split it into my ions, so I'm always going to have H plus for acids. I'm going to have everything else as my anion, so I got to make the opposite charge. And then what is this called on your polyatomic ion chart? That's right, good. This is nitrite. So I get rid of the ite, and because it ends in ite, I add us acid. So this is nitrous acid. How about these sulfur and phosphorus containing compounds? In these cases, what I would change my stems to, and we'll see this when I write this out. So this right here is sulfite, and this right here is phosphate. If I erase the ite part, oops, I didn't lift my pen for that, I guess. And I erase the 8 part there. I get these as my stems, sulf and phosp. But apparently, that doesn't sound very good to chemists. So we add extra letters to those stems to make it sound better. And so now what we can do is then do the name. So instead of sulfurous acid, it becomes sulfurous acid, and this becomes phosphoric. So this one right here, H2SO3, would be sulfurous acid. And H3PO4 becomes phosphoric acid. Why? Just to confuse first-year chemistry students, I guess. I don't know. I need a hotkey to erase all ink on the slide. That would be useful. All right, let me put a bunch of acids on the screen for you. Here's what I want you to do. So on the top set, look up the polyatomic ion and type in the name of the acid into the chat once you got it. Okay? Remember the rules. You're going to have to do all of them here because I've sort of scrambled them in. Down at the bottom, you have to turn those acid names into formulas. This is admittedly a lot harder. So do the rules backwards. Let's do an example of that with sulfuric acid, because you know what the formula should be here. So sulfuric acid, we're going to get rid of the ic acid, and then we'll get rid of the extra stem that we add for that. Since we used ic as our prefix, this must be an acid that contains sulfate, which would be that. With that information in mind, you should be able to write the formula of the acid, okay? That's the formula that you want to go through for doing that. So write out the names and then determine the formulas, and we'll go over the answers in about 5 minutes or so. So we'll see you in a bit. All right, just another minute or so to go before we go over the answers. All right, let's start naming these acids. So first we need to look up what all of these polyatomic ions are. So ClO4 is perchlorate. So we get rid of the 8. And for 8, you put in ic acid. So this becomes perchloric acid. For my bro here, this is hypobromite. Get rid of that ite. Hypobrom plus acid. This is dichromate. Get rid of the 8. Dichromic acid. This is cyanide. Remember that ide is not ite or 8, so we got to get rid of that. And we got to put it hydro cyanic acid. That was the exception on the first page. What the heck was that? Oh, that was a bird outside. Just flew right up next to my window. And then finally here we got phosphite. That's an ite. We get rid of the ending there and put us acid. So phos. And then for phos, remember, we got to add or. Oops, I missed an O there. Eraser. Phosphorus acid. Now, spelling with these acids and phosphorus gets kind of weird because phosphorus has this extra O here, but the element phosphorus, this is the element spelling. And you'll notice that there's no O right there. But in phosphorus acid, there is an O. Be careful you don't misspell them on the exam because Canvas, again, is picky. I do set it so that you can make like 1 or 2 character swaps. Like if you invert 2 letters, it should give it to you. But if you make too many mistakes, it marks it wrong. All right, so for this one down here, why is HCN an exception again? So HCN ends in ide. Just like all the binary acids do, they all end in ide. So chloride, bromide, iodide, cyanide. So it follows that same rule. Going back over here, we got sulfate, which I looked up on the table. H plus comes as that, H plus, so I need at least 2 of these to neutralize it. So the formula becomes H2SO4. Sure, no problem. Let's do the same thing down here. So I've got nitric acid. I'm going to get rid of the ic acid. Ic acid is the replacement for 8. So I have to look up nitrate. That's this. If I give it an H+, I would then get HNO3. That's nitric acid. We got chromic acid, so again, same thing. That's chromate. There's the formula for chromate. So I would write this as H2CrO4. Down here I have hypochlorous acid, so I can get rid of the us acid. That's the replacement for ite. Hypochlorite is this. So that must be its acid. And then same thing here. Here's ic acid. We'll get rid of that. It's periodate, not periodic-ate or whatever. So be careful. Some of these acids look like words, especially with iodine in them, and they can be confusing. So periodate is IO4 minus. So the formula ends up being HiO4. So periodic acid has that formula. Not periodic acid. There's no such thing. All right, so that's all the rules for naming. So there are, excuse me, there are rules to name ionic compounds, there are rules to name covalent/molecular compounds, and there are rules to name acids. Each of them has their own little gimmicks and tricks that you have to adhere to. With ionic, you have to remember Roman numerals for variable charge metals. With covalent, you have to remember the numeric prefixes. And then for acids, you have to remember all these funky rules. So be very careful that you apply the correct rule to the correct thing. All right. There is a giant worksheet that just has tons of these. I think there's like 3 or 4 pages of names. So definitely practice that because your quiz is just naming for Unit 11. Other than that, it's time to celebrate. Hooray! What are we celebrating? Oops, I didn't actually... What did I hit? Oh, I hit back on accident. Well, we can celebrate again. There we go. This part of the screen will just go blank for a second because I have to... Oh, it completely closed it. Look at that. I have to load the next set of slides. Which is these. Oh my goodness, now there's just crows outside. Usually I don't have crows outside my window, but... It's like all the animals are going insane today. Alright. So go ahead and grab the slides for Chapter 12 real quick. You're also going to want to grab a calculator because this section of the course contains math. That was why I was stalling there. Just to get that sound effect. Yep, we're going to do math. In fact, I got to get a calculator too. Mine's right here. Make sure that the battery on it is okay. Yeah, cool. Something to note. If you don't have a calculator that is handy or does exponents very well, here is what you want to do for that. Wolfram alpha. So you go to this website. I don't know where my capture is on here. Desmos is another good one. I personally like Wolfram Alpha because it shows you what it is trying to do with the math. And also, Wolfram Alpha does a bunch of other random stuff with it, too, that I'm not aware of, that you could just, like, experiment. Like, it could probably tell you, like, formula mass of C2H6. I don't know, we'll do that. Give me the density. That's not what I wanted. But... There's a bunch of interesting stuff on here. Yeah, Wolfram has a lot of features, so you might not want all of those features. But what it's really good at is if you have to do something like I don't know, 12.36 times 1.88 times 10 to the 20 or 23rd. And I actually put an X here. I gotta do that. Divided by 3.14159. I don't know, something like that. So if you do this in a command line prompt, it will actually show you a picture of what it thinks you're trying to do. And then you can match that up with your result on your paper, which is kind of nice because your calculator doesn't always know what you are intending for it to do, especially if you're doing something like this. So 47 minus 42, and then I want the result to be divided by pi, I guess. If you type it in like this in your calculator, this is actually what it thinks that you're doing, and that's not at all what you want. What you really want is that. And so now it shows you that on the screen. So that could be really useful. If you're having trouble, like, doing a calculation, you're like, why is this giving me the wrong number? I don't understand. It's usually because you're not using enough parentheses on the calculator, but on Wolfram Alpha, there's at least a visual representation of that. So I use Wolfram Alpha if I'm trying to do a really, really big equation, or if I have to do like a system of equations. It'll just solve it for me instantly. So, all right, let me get rid of that. The other thing that I want to show you will be, oops, let's go back to here really quick. So this, Lentech molar mass. There we go. And it's not going to zoom in correctly, but there we go. So this website, Lentech, oops, it kind of didn't actually show the whole thing, gives us a molecular weight calculator, which we're going to be using to determine the atomic mass of molecules, which will be the molecular mass. And this first section that we're going to do is going to show how to do that on the periodic table. And then we're just going to go to Lentech, and we're going to be like, okay, well, what's the formula mass for calcium? We'll just type in Ca there. Okay, it's 40.08, which you could tell by looking at the periodic table. But what if I wanted to get, like, the formula for Ca3PO4-2OH6? I don't know. Like, some ridiculous ionic compound. I could just hit enter and it's done. So what that's doing is it's adding all of those masses together for me. And then there's the result to 2 decimal places. So Lentech will be super useful for you. Let me put the link to Lentech here in the chat in case you want to bookmark that. And then let me put the link to Wolfram Alpha in the chat in case you want to bookmark that too. Those are just links that I have handy that I use all the time. So I might as well share those around because that, oops, I didn't mean to advance the slide there. Though that's just information that might be helpful, and if you like it, that's great. If you don't like it, you prefer your calculator, or you prefer you're just looking it up on the periodic table, that's fine too. You can do whatever you want to. I'm not going to mandate that you specifically use one site over the other. Those are just the ones that I've found and I like. So in this first section, we're going to talk a little bit about determining molar masses and formula masses. And then we're going to go into a topic called percent composition, which just tells us the makeup of something in terms of its constituent parts. And we're going to calculate percentages of stuff using that. Later on, we're going to take that information and put it into a different calculation with the mole, which is the next topic that we're going to come up to determine formulas of compounds. Okay, so the whole point of chapter 12 is to start getting introduced to, okay, here are those numbers on the periodic table. Let's start making practical measurements of stuff using dimensional analysis. And if you were wondering why at the start of the quarter I made you do all these problems about orcs carrying gold or dwarves driving their Harley-Davidson motorcycles down the highway, and calculating gas mileage or whatever. This is why. The whole point of making you do all that crazy dimensional analysis with units that don't seem to make sense is because now you're going to get to the units that are just new. And we're going to have to do dimensional analysis with them. Okay? So, that's what we have to look forward to. And this is how it's going to be for the remainder of the quarter. So units 12, 13, 14, 15, 16 is just all this. So buckle up, because here we go. All right, way back in Unit 7, which feels like it was a long time ago because it was, we figured out the mass of elements off the periodic table and then said, okay, that's their mass in AMU. So, for example, if I grab my periodic table, and again, you should have a periodic table handy or some link or something to one, like p-table, for instance. If I looked at, say, nitrogen, I would see, oh, nitrogen is 14.007 AMU. What is an AMU? It was the mass of a proton or a neutron, roughly speaking. So like a proton or a neutron would weigh roughly 1 AMU. They're a little bit more than that. But to 1 sig fig, like, that's fine. In fact, to 3 sig figs, it's about 1 AMU. If you want the mass of a formula, all you do is add all the masses of the elements together. So here's an example. If I wanted to give you the mass of this tin fluorine compound, tin 2 fluoride, actually, I would take the atomic mass of tin, and then I would add 2 fluorines to that. Now, the periodic table I'm using when I did this only went to 2 decimal places, which is fine, because when I do addition, it's going to go to 2 decimal places. Because remember, when I add, I go to the most precise... Oops, that's not my pen. I go to the most precise place. So this is the 100th place, this is the 100th place. My answer goes to the 100th place. Your periodic table, excuse me, may have more decimal places. My strategy is to use all the decimal places that you have, put it in the calculator, and then when you report the number, report it to 2 decimal places. And that will be sufficient. However, make sure that you have at least 4 sig figs in your result. So, for instance, if you looked up H2, H2 is 2 hydrogens. A single hydrogen atom is 1.0079. I would just type in my calculator that number times 2, and I'd get 2.0158 or something like that. I'm trying to do it in my head. I would then just keep 4 sig figs, and that would be good enough. If you wanted to keep more, you could. The reason I'm telling you this is because when I set an error range on Canvas for the answer, I want to make sure that you fall into the correct error range. And if you use too many significant figures, you may end up with an answer that's too high if you just did that forever. So make sure you're applying the correct sig fig rules as you go. But because periodic tables have different numbers of sig figs that they report, I just go to 2 decimal places as long as I have 4 sig figs. All right, so I'm going to put this on the board here, and what I want you to do is first try calculating it with your calculator in a periodic table. Then go to Lentech and type it in and see if you get the same answer. You should get like 60.06 or something, I think. Let me, I might be thinking of a different compound. Let me just do this on my own here. Yeah, you get about 60.06. And then if you have extra time, try drawing the Lewis structure of that. Because this is actually a Lewis structure you could draw. All right, so what number did you get? And there you go. That's good enough for our purposes, yeah. My answer on the screen only has 2 sig figs or 2 decimal points because so do most of my answers when I did the addition. So if you used numbers from a periodic table that had all of these in the hundredths place, you'd get my answer. But if you had a periodic table that had all of them in the thousandths place, or even more than that, you could get more decimal places. So there will be a range of sig figs for these answers. Okay, so here are a bunch of compounds. I want you to determine the formula mass by punching them into Lentech or calculating them on your own, however you want to, just to get into the practice of doing this. Because this is going to be like the first step that you do in any of these problems that are coming up. And so we need to have a resource on hand because otherwise we're going to be eating up all our time just adding numbers together, and that's trivial. So go ahead and report these numbers in the chat, and I will do them on Lentech with you in just a second once you've had a chance to look at it. Oh, don't let your dog sit on the keyboard. Maya loves the spacebar because it's the biggest key. She likes to stand on it. That's a lot of commas. With the number of people that are watching, that would be like everybody gets 12 commas. Let me resize this window here so that it fits next to... Oh, I don't want Wolfram Alpha anymore. I want Lentech. Alright, so I'm going to just type these in here. So AlCl3, you should get 133.34. I'm not sure how visible that is. Let me crop this down. We'll just make it bigger. There, I could definitely see that now. And we got barium hydroxide. So when you're typing into Lentech, make sure you're typing in the correct elemental symbol. So like if I typed in BA with a capital letter, it gives me an error that says formula did not parse correctly, which you can't see, but if I do this, you can see it up there. Formula did not parse correctly. Because it doesn't know what element capital A is. So barium hydroxide is 171.34. If you got 133.33 on your calculator, that's totally fine. That's within a reasonable error. Remember, being plus or minus 1 on that last digit is totally normal. And the reason I'm saying that is based on these numbers that I'm generating here. The numbers that Lentech might have programmed into its periodic table might round slightly differently due to either like operator error when they programmed it, or maybe we've updated a periodic table since and they haven't updated theirs, or something like that. Ammonium phosphate, I got 149.09. And tetraphosphorus dicoxide, 283.89. And you could do literally any combination that you want to. So I could do uranium 292, platinum 486, chlorine 735. And if I were to put all of those together, the atomic mass would be 190,000 for this crazy, crazy, crazy molecule with 292 uranium atoms in it. So you could do any sort of formula you want. I could probably make a number that overflows this. So like oxygen 999999999. Yeah, it doesn't know what to do if I do get to that point. Anyway, that's Lentech. And that's formula masses. So we're going to use this information a lot. So have Lentech handy to use. Oh, excuse me. I didn't manage to mute the mic in time there. I just tried to block it. It's already 3 p.m., so I'm going to advance to the next slide for a second, and then I'm going to put this on the screen. Let's take our 10-minute break here. I'm going to go hug cats because they're probably sulky. So, and then let me get the Mega Man music back out here. We have Mega Man 10 today. I'll find a different game to do music from, but the chiptunes are just so good. Alright, I'll see you all in a bit. Oh. It is possible to actually land exactly on 10. I did it once last quarter, and it was exciting. We'll go back to here. Oh, I need my phone to not be sitting on my knee, because it will fall over the second I lean forward to write. Excuse me while I stretch. All right. What we're going to do is we're going to use the percent by mass formula and formula masses to figure out percent composition. Now, you should probably remember that percent by mass, which was like mass of the important thing that we care about over mass total, times 100%. That formula is going to be used here. We're going to use that in problems like... Oh, I guess I haven't actually shown you that formula here. So I thought we went over that earlier in the quarter. I guess not. For example, I could ask you a question such as this. If I give you like a pound of water, we'll say, what mass of that water is oxygen? And you can actually answer that. And the way that we would do that is the following. So let me scroll this up. So let's start by writing down that formula. So percent x is equal to the mass of x over the total mass times 100%. So in this case, we're going to look at oxygen. And it comes from H2O. So that means that the oxygen's mass is going to go there, and the water's mass is going to go there. So if I look on the periodic table, oxygen is 15.999. AMU. If I want the mass of water, I have to go to Lentech. Do I still have Lentech open? I do. It should be 18.02 is what they gave me. So we'll punch that in the calculator. 15.999 divided by 18.02 times 100% gives me 88.7846. So the number of sig figs that I have on here, I can conclude that water is 88.78% oxygen by mass. And by extension, any mass of water that I give you will be 88.78% oxygen. So for that 1 pound of water that we just had before, of 1 pound of water, 0.8878 pounds would be oxygen. The other 11.3% or so would be attributed to hydrogen. When I did this calculation at home, apparently I got 88.80. That's close enough. Again, if you use a different source for your mass, you will get a different result. In fact, I used two sources for my masses. I used my periodic table from Web Elements on my desk here, and then I went to Lentech to get the mass of water. So try to avoid doing that if you can. Try to use one source for all of your calculations to minimize error. All right. Let's do another example. Let's determine the composition of aspirin. What percent of aspirin is each of these elements? So carbon, hydrogen, and oxygen. I have to change where this is capturing. So we'll do that. So we're going to do the same thing. So my percentage of carbon would be the mass of carbon over the total mass times 100%. How many carbons are there in this aspirin? So there's 9 times the mass of each carbon, which would be 12.011 AMU. Now the 9's important. You got to include the 9 because you have more than just one carbon in your total. Down here on the bottom, you include the 9 also, as well as the H8 and the O4. So I'll go to Lentech and type in aspirin, I'm going to type in its formula. C9H8O4. It says 180.16. Let me undo that. AMU times 100%. And I got 60.002% carbon. All right, let's do the same thing with a different element. Let's do hydrogen. Same formula, except in this case, we're going to be looking at the mass of hydrogens instead of the total mass. There are 8 hydrogens in here, so I'd go 8 times 1.0079 AMU. Again, those masses are just off the periodic table. And then let's look up the total. Oh, I don't have to look up the total mass because it's the exact same as it was before, right? It's still aspirin. When I do this, I got 4.47557. Oops, hold on. There we go. Now I can do the last one. We can do oxygen here. Let me get darker color than that. So percent oxygen. And there's 2 ways to do this. I could just say 100 minus the other 2 and get an answer. And you'll get an answer that's right there with what we're going to do. But I'm going to just show you the formula anyway because that's kind of the whole point of this set of problems. And you're right. When you add them all together, you should get really close to 100%. Will you get exactly 100%? No, because of error. So I get 35 point... Oops, I didn't write times 100% here. 35.522% oxygen. Now, when I add all these together, I'm going to go to the thousands place, thousands place, thousands place. So my answer will be in the thousands place. 60.002, 4.4756, 35.522. And I got 99.9996. Well, that last 6 actually gets rounded away, and it ends up being 100.000. So that's close enough for our purposes. So that's how we do that. Notice that on the screen I have different decimal places because I used a different periodic table. All right, let's answer some more questions about this. What's the formula of ibuprofen if these are the percentages and this is its formula mass? So we went forwards. Can we go backward? Can we figure out the formula? How the heck do we do that? Oops, hold on. Oh, I'm too big here. Oh, that's not ideal. What? Undo. Undo. Oh, no. Where did it go? Okay, well, hold on. I know that name is already in use. Oh, you know what I could do, though? Hold on. Sorry, I just need to capture this here. Copy. Paste. Duplicate. Okay, and then I want this down here. Is this okay? This does what I want. Okay, that'll make it go behind. That's not what I want. That's what I want. Okay. Sorry about that. I lost the PowerPoint thing because I shrunk it down too small and it became one-dimensional or something bizarre there. So I need to be in this window. I could do that. There we go. Okay. All right. Going backwards is a little harder, isn't it? But it turns out it's actually not that difficult if you just write out the formula with what you know. So let's do that. Let's start with carbon. So I know that the percent of carbon is equal to the mass of carbon divided by the total mass times 100%. So let's look at these things, and what do we know? So we know the percent of carbon, we know the total mass, and you know what this is, but we don't know how many carbon atoms are in there. All we know is that the mass of carbon is going to be some number of carbons times the mass of carbon itself. Well, if I know the percent and I know the total mass, I could then solve for the mass of carbon, and then I could eventually solve for N, which would give me the formula, or at least the number for carbon. And we just do this 3 times. So let's do that. So I'm going to rearrange my equation here. So I got percent carbon times the mass total divided by 100% equals the mass of carbon. And so that's going to be, what was the percent of carbon? It was 75.69%. Notice that I'm putting this in as a percent. And the reason for that is because when I divide by 100%, these will cancel out. and you end up with a decimal. So that's where the decimal comes from. Times the mass total. And so the mass total is 206.29 AMU. And so what I got from that was I got 156.14 AMU is the mass of carbon. Now, carbon doesn't weigh 156, but a bunch of carbons could weigh 156. So I'm going to divide by 12.011 AMU per carbon. I could show the dimensional analysis if you want me to. This is what I'm doing, but we all know that, oh, I have this many, I'm just going to divide. So I divide by 12.011, and the calculator spits out this number. Now, specifically, it shows this number, 12.9998. But we're only going to 5 sig figs anyway, so it rounds up to 13. So we now know that there are 13 carbons in ibuprofen. So I'm going to write that up here, C13. There, we got that part. All right, now we're going to do hydrogen and oxygen using the same method. So let's scroll down and get some more space here. Get a new color. So let's do hydrogen here. So I know that hydrogen is... I'm going to just fast track to the same formula that I had before. Oops, hold on. And again, that's just me rearranging the formula that I used before. So if this is my mass for carbon, here's the rearranged formula. Oh, sorry, that's up here. So here's the rearranged formula. And so that would be 8.790 over 100% times the total mass oh, I messed up in my calculator here. Times 206.29. So that's the mass of H. But what is the mass of an individual H? It's that. So we'll divide by 1.0079. And the number that I get is 17.990, which rounds up to 18. That's close enough to 18. And then we'll do the same thing for oxygen. And so that's 15.51% over 100% times I keep looking at the numbers, trying to find the one I want. It's the same one every time. 0.1551, 20629. And I get 31.996 AMU. Divided by the mass of a single oxygen atom. And I get 1.999998, which is just 2. And so there's our formula. We should get C13H18O2. And using that information, if we go to Wikipedia, we look up the molar mass of ibuprofen. So ibuprofen, Wikipedia. And I capture this screen. And I actually make it show up. We find out that the molar mass of it is, or not molar mass, but the formula is, I can't make it bigger by holding that button there. There we go. C13H18O2. So our data supports the actual formula. We successfully calculated the formula based on that information. I personally think that it's really cool that you can do this calculation and have it work out like that. All right. Here's another type of question that I can ask you along these same lines. And you're going to notice that there's like this wide variety of question types, but they all use this formula. Okay, so you got to know how to manipulate this formula to get what you want out of it. What mass of hydrogen is in 20 grams of acetone? Here's the formula of acetone. What is this? This can go away. There we go. So we're going to do the same thing. First, I want to figure out what percent of acetone is hydrogen by mass, and then I'll just multiply it by 20 grams. So here we go. So percent hydrogen will be mass of hydrogen over mass total times 100%. And so that's going to be, how many H's are in acetone? Well, I counted 6, so double check that to make sure that I didn't miscount. And I got to find the total mass, which that's why we still have Lentech on our screen, right? 58.08 is what I got. Times 100%. And when I do that calculation, these cancel out. And I get 10.412, so 10.41% hydrogen. Now, I'm going to grab a different color here, and I'm going to write this expression in a different way. So this expression has the same meaning as if I said that in 100 grams of acetone, there would be 10.41 grams of hydrogen, right? Because that's how percentages work. It's out of 100, yeah? So if I use this relationship right here and multiply it by, say, 20 grams of acetone, that's like multiplying by my percentage to figure out what percent is hydrogen. But this way, the dimensional analysis shows how the units cancel out here. So grams of acetone cancel, leaving grams of hydrogen. And so I just get my decimal and multiply it by 20. And so the answer I get is 2.08 grams of hydrogen. So in a 20-gram sample of acetone, 2 of those grams are hydrogen. And that makes sense because it's supposed to be about 10%, yeah? So there you go. It's probably the most examples that we've done on a single topic before I have you just do it. And guess what? I have another example. In fact, I might even have 2. Oh, no, I only have 1. Okay. Here's the last example. A molecule with only 1 carbon atom is 74.8% carbon. How much is the entire molecule weigh? And so what this is asking us to do is figure out the molar mass the formula mass of the entire molecule with little other information. So again, our strategy is the same. Let's write down the formula. So I know that the percent of carbon in the sample is going to be equal to the mass of carbon over the total mass times 100%. Well, what terms do I know? I know the percentage of carbon. I know the mass of carbon because there's 1 carbon atom in the mass. And this is just a number, so I'm going to be solving for that. So I'm going to rearrange my equation. So a total mass will equal mass of carbon over the percent of carbon times 100%. And then the percentages will cancel out when I do that. So let's punch that all in. I have 1 carbon atom, and the mass of a carbon atom is 12.011 AMU. My percent carbon is 74.8%, and then I times by 100%, and these percentages go away. So the whole thing must weigh 12.011 times 100 divided by 74.8. Now, because I was calculating the total mass, I should get a number that's bigger, and I did. I got 16.057, which based on the number of sig figs, I only get 3 sig figs. So what does this tell me? Well, it tells me that I have 1 carbon in my formula, and that the whole thing weighs 16.1 AMU. Well, I could then conclude that X must be whatever 16.1 minus 12.011 is. And that's this. And then I could look on the periodic table for anything that weighs 4. And it turns out that there's only 2 possibilities. So I've either made the first helium compound, or I have this. And that's probably what this is. Now, that's an extra part of the problem that I did not assign to you. But the point of that is to say, okay, if you can get these calculations where you learn these properties about molecules and the elements that make up them, you can then get to the formula. And for a lot of people, there's a disconnect between, okay, I understand that these are numbers that we can manipulate, but how do I know that that's what the molecule actually is? I can't see the molecule, and I can't, like, grab it with my tweezers and be like, oh, there's 4 hydrogens connected to this carbon. How can I be sure? And the answer is, this pretty much verifies what the molecule is. We're using numbers and data that we verified over and over and over again to then apply to molecular formulas and conclude that, hey, if this percentage is my compound, I must have this in there. And so this substance that we identified in this problem was methane. In other things making sounds during lecture news, somebody is sitting there just hitting their car alarm over and over. So that's a thing that exists. All right, I've shown you all the different types of problems that I can do for this. So what I'm going to do is I'm going to give you 3 of those problems. And I want you to try and solve them. And this is going to take a considerable amount of time because this is where the class difficulty like ramps up, by the way. So this is the last thing that we're going to do for today, and even though there's 20 minutes left, what I want you to try and do is start working on these problems. Ask me questions in the chat. Let's number the problems so that we can refer to them in a more simplistic manner here. Try these 3 problems. When you get the answer, put it in the chat. If you get stuck, ask me a question about it. I'm happy to help you. That's the whole point. But remember, the whole point of this lesson was to apply that percent formula. So at the start of each of these problems, write the formula down, and then see what you know. Put little check marks by stuff, and then solve for the other thing, and then work from there. Okay? Good luck. We're all counting on you. See you in a bit. How are we all doing? Any questions? Let me know in the chat. How many sig figs for the AMU of nitrogen? It depends on the periodic table that you're using. So if you're using my periodic table, for example, I go down to 14.007. So you could probably get 5 out of that. On question 1, would you make the formula for ammonium phosphate or just use the individual ions? Use the entire formula. Which means you have to look up the polyatomic ions for ammonium and phosphate and then write the correct formula. Notice how I'm slowly starting to take all of the stuff that we've learned and put it together? We've been learning all these like isolated pieces of information for so long, and now it starts to come and sort of crystallize into this bigger picture, and it's kind of a beautiful thing. Which is why I love teaching this stuff, is because it's like, oh, this is why we've done all of that so far. All right, I'll shut up now. We'll let you guys work. Let me look. Let me do the calculation real quick. So AMU for ammonium phosphate, NH4, 3PO4. I got 149.09. So if you are using sources that have more decimal points, then you could definitely get that 087 on there. I'm just using Lentech because it only gives me to the hundredths place. I can only report to the hundredths place. I would say your answer sounds correct. I think what I'm going to do... Oh, I have some people with answers coming in. Okay, cool. It sounded like most people were still working on number 1 and maybe number 2. I don't want to like interrupt people while they're doing these problems because I feel like this practice is kind of the whole point. So what I think I'm going to do is I'm going to just hang out for the next 9 minutes because that's how long we have left in class. We're going to go over the answers first thing on Tuesday. So I won't do the answers for these 3 problems today, but I'm going to give you some time to do it. Actually, you know what I can do? I could probably just... I'm going to give you the answers, but we're going to go over how to do them on Tuesday. So let me just do these really quickly. Yeah, Lentech totally does, and that's actually what I'm copying down for the for problem number 1. So oh, I'm not muted. Okay. I'm just sitting here working quietly and thinking. I'm going to put the answers on the screen here, so you can pause the video if you want to keep looking at these questions. But here's the answers to these problems. So number 1, I have the percent breakdown written there. You can get that directly off Lentech. Number 2, there's the answer to that. There's that much sodium in that sample. And then number 3, there's the mass of that compound. Which, as a student pointed out, is probably N2O. I would say that that's extremely likely. I mean, it could technically be if there was something that weighed 8. There's not. It could be CH4N2, because that weighs about 16. But the simplest answer is almost always... Does number 3 ask for the formula? As for the formula mass, so I just want to know how much it weighs. But you're right in that you can predict that it's N2O. Like, for sure. I would bet money on that. Okay, we've done a lot of calculations today. So, any last minute questions that you have for me before we call it a lecture? Let me know in the chat. Let's talk about what I'm going to do over the next few days. So I'm almost done with lab number 2, finally. I've got 3 of the 4 sections done, and then I have to go back and pick up the ones that there were like formatting errors, and I had to get a new copy or whatever. So I will do those. Those grades will get posted this weekend for sure. I will get quiz number 6 online probably tomorrow, and it'll be due Thursday as well next week. Yeah, lab number 3 due Thursday, the 12th. Make sure to get your quiz number 5 in by the deadline. Try and do that tonight if you can. Definitely before last call tomorrow. Okay. All right. I guess that is all she wrote. So have a wonderful weekend. Oh, what do we got here? Quiz 6 is based off of Unit 11. Yes, so Quiz 6 will be entirely naming. Which means that you're going to see a bunch of questions, and there's probably going to be some repeat questions in there. Just because of how I have to generate the quizzes. I can't make it so that you just have one name equals 1 point. So you're going to see a bunch of little questions. But I had to fiddle around with it, so we'll see what happens. But in any case, I will do that tomorrow, and I will see you all next Tuesday. Have a great weekend.